Hi, we are continuing the discussion of building digital electronic gates, now we are looking at the family of diode transistor logic. And the diode transistor logic also depends on controlling the, uh, s- the state of a BJT device, all right? And this is um, the device that can be either in the cutoff state or forward active or saturation state based on the VPE voltages. Okay, so the VPE voltages control the state of this BGT device, and we will do that based on two back-to-back diodes, and we'll see how that happens. Here, basically, we have here back-to-back diodes. Okay, so let's see how we do this. Um, so basically, we have here a this is our BJT device, right? And the emitter connected to ground, obviously. And then you have the base with a diode here, okay? And then opposite to it, there's another diode, and then we have the VN right here, okay? The input voltage. Over this node, we have the RB, and over the collector, we have the RC, and both of them are connected to the power supply, which is VCC. Okay, typically VCC is 5 volt. The important node here to notice is this node VX here. And Vx, if we want to write the logic, the Kirchhoff voltage law for this thing, for the node Vx, we will see that the voltage across this diode plus, which is here referred to as VDI, and the voltage across this diode, which is referred to as VDL. So VDI plus the input equals VDL plus VBE. We are going to say roughly here that the voltage of the diodes sort of cancel each other for very simple analysis, and therefore we can see that the input voltage controls what? It controls the VPE voltage, and therefore whatever voltage we have, we can control the VPE. So for instance, if we have a voltage of 0.6 volt on the input voltage, it will be reflected as 0.6 volt on the VPE, and that will force the device to be in the off state. On the other hand, if I have on the V input 0.7 volt, it will be reflected as 0.7 volt on the VPE for the BGT device. So this guy will move from the off state to the forward active state. And if I change the voltage to 0.8 volt, the forcing 0.8 volt on the VPE, it will move to the saturation state. Okay, so in brief, what we can say roughly that the input voltage, right, controls the VPE, right? That's the summary of this analysis, and that's how this DTL logic works. Okay, so let's now let's take a look at case by case. Okay, so see for example here. Okay, so let's uh, erase some of this now and take a look at the case by case. Okay, the case by case. Whoops, gotta go back here. Case by case, and see the equations, because we need to be convinced that things are going to work on a case by case basis. Now let's consider, for example, when the V input is less than 0.7. So let's, for example, assume, okay, um, say for example, let's assume that the V input equal zero point 0.6 volts. Okay, so this, let's say it is zero point 0.6 volt, zero point 0.6 volt. Okay, and therefore the VPE here, the VPE here, the VPE here, the VBE here. So this means that the VBE will equal to zero point 0.6 volt. Therefore, the BJT is in what state? It is in the cutoff state. If the BJT is in the cutoff state, it means that I will have this, the output voltage here equals 5 volt, assuming that the current here, IC, equals 0. Okay, so that's the end analysis. So notice that here, if we look at the curve here, meaning any input voltage less than 0.7, it will be considered as low, right? And it will be giving me an output of high. Okay, any voltage less than 0.7. Right. So let's now consider the other case where I change this input voltage to zero point 0.7 volt, and that means that the VPE here will equal to zero point 0.7 volt, which means that this device here now will change from off to forward active. And in this case, I will have a current which is non-zero flowing through the RB and flowing through the RC. Okay, and I can compute the value of the IB, right? Because the IB here. So let's look at it here. So um, the value of the IB is the following, where you will have a um, the value of the IB. I can run the Kirchhoff voltage law through this here, so I can see VCC equals IBRB plus the voltage through this diode, which is V DI, plus the V input, right? This is known, this is known, this is known, and this is known. Now I can solve for IB. And once I solve for IB, I can say data times IB equals IC, and I can find what is IC. And then I can find the V out, which is equal to V out plus IC times RC equals VCC, which is the 5 volt. Okay, I can find out what is the V output. And you can see here in the diagram here, this is here the transfer characteristic curve. When I have a small voltage of the input, the output is high because the transistor is in the off state, and then by increasing slightly the input, you can see the output goes down. This is because the ICRC grows, it will reduce the value until I get to this point. And this is the point when I establish, and this is the point when I establish the value of the V input to be 0.8 volt. When the V input equals 0.8 volt, then the VPE will be equal to 0.8 volt, and the voltage and the state of the transistor here, it will change from forward active to saturation. And in saturation, what I have, the value here of the output uh, will be equal to zero point 0.2 volt, because that's the description of the saturation state. It short circuits the collector to the emitter with a differential voltage of zero point 0.2 volt. And I can see that once I reach the saturation here, I have zero point 0.2 at the output. So this value here equals zero point 0.8 when I enter, and this value here is 0.7. So to summarize the characteristic curve, anything less than 0.7, the output is high. Anything above 0.8, the output will be low, and it is equal to 0.2 volt. Okay, so this is basically the DTL logic, right? And its behavior, very straightforward. And again, it all depends on our understanding of the VX node. Okay, all right. So we control the VPE through the voltage of the VI. Okay, so let's go back to the here. Now we can construct an AND gate where the voltages through any one of those inputs will control through any of those inputs will control the through any of those inputs will control the VPE. So this is an AND gate. Any one of these inputs is low will force the transistor to be in the cutoff state. Okay, and then the output will be high. And if both of these inputs are high, okay, then uh, uh, the output of this gate will be low. Again, just to reinforce what we mentioned a minute ago, that when one of these voltages is low voltage, okay, which means below zero point 0.7, this forces this transistor to be off, right? And therefore the output becomes high, okay? And if let's see if we choose a different color here, and um, if both of these inputs are high and high, both are high, and therefore we are which means above the zero point 0.8 volt, then we will have a established a zero point 0.8 volt here, and this would be instead of off, it will be in saturation, and therefore that will have a zero point 0.2 volt here, which makes the output to be low. Okay, and therefore it's important for us to understand one thing for every type of logic, is that the notion that what is low and what is high. And in every family, we have to understand that as long as you are below this voltage here, which is zero point 0.7, your input is considered to be low. And if your input voltage above the VIH, so this is VIL, if it is above the VIH, you are considered to be a high. So that's, we're talking about the input voltage. All right. So this is very important here in these uh, transfer characteristic curve, that they always talk about what is the limit for the low input voltage and what is the limit for the high output voltage. Very important note that we have to keep in our mind as we go through these families. Keep those 2 points in. Okay, the next family to be discussed here is the TTL family. And the TTL family is one of those very popular for the BGT devices, and it has been used for sometimes. In fact, you can find some of the chips use this family. And let's explain the main principle behind this family. Well, here is our output transistor. We are used to this output transistor, and we know that this transistor goes from the states of forward, active, and saturation. And the trick is to play or to change the value of the VPE for this transistor. Now, to do this, we have seen different ways, resistor, we have seen diodes, but in this type of family, what we do is that we use another transistor here, okay, another transistor, okay, where is connected as such. So this is the input voltage here, and this is the output voltage here. And watch what we will do right now. The VBE here, okay, the VBE here, the VBE equals the VCE for this transistor, and this transistor typically we refer to it as the input transistor. And this one would this is the Q1 and this is the QI. This is the VCE. Notice that this is the collector, this is the emitter, okay, plus the V input. Okay, so this is the equation that controls. This is the equation that controls the VBE for what? For Q1, meaning this transistor, and this is the VCE for which one? For Q input, which is this transistor. The trick is always in these type of circuits is that you want to control the VPE of what? Of this transistor. You want to control the VPE of this transistor. That's the trick in all of these circuits. Okay, you want to control the VPE. Now, okay, so now we know the equation. So here is the input that I can control. What about the VCE? In TTL, the VCE of or let's say the Q input, this transistor is always in saturation. Beautiful. Which means what? Which means always this is 0.2 volt. So now if this is always 0.2 volt, it means that whatever value I add to the input voltage, add to it 0.2, you will get the VP of this transistor. So for instance, if I want this transistor to be in the forward active region, I just place the input to 5 volt. That's it, right? And 5 plus 0.2 equals 0.7 volt. Therefore, this transistor is in the forward active. Well, if I want to have this transistor in the, let's say, for example, I want it to be in saturation, change 5 volt to what? To 0.6, and that makes that this is 0.8. So this transistor is in saturation. Okay, so I think now we know clearly what's the idea. In fact, you can see here in the characteristic curve, right? If I have 0.5 or less, this is the input. If your input is 0.5 or less, this is considered to be low. Okay, but if you have 0.6 your input, this is considered to be high. 0.6 volt or higher on the input. Now we are describing the input. Watch, we are describing the input, right? If you have 0.5 or less, your input is considered to be low. If you have 0.6 volt or higher, your input is considered to be high. And watch what happens to the transistor here. If you have 0.5 or less, your input transistor, which is this one here, okay, is what? In what state? It is in the off state, okay, and therefore the output is 5 volt. Versus if you have the input 0.6 and higher, then your Q1 is in saturation. This guy is in saturation and forcing the output to be 0.2. Let's go into a little bit more detail. Now we explained the general idea of the operation of the device. Let's take a little bit more detailed analysis, okay, and see bit by bit what happens for every case of the input. Again, and because we are controlling the input voltage with an input transistor, that's why this family of transistor is called TTL, transistor to transistor logic. You are using two transistors to implement the gates. And in all these circuits, you can see that we are implementing an inverter, and then we expand to other logic gates of NAND, NAND, or NOR, and etc. But it always would like to start with an input. Okay. Okay. Let me see. Take a last bit of so let's go back to our pen here and use let's see here, use so let's draw the circuit here. So here I have my VC C, which is typically equals equal 5 volt, okay, unless you are specified other than this value, okay. And then so have here, this is my resistor, okay, which goes to the base of this transistor, okay. And this is my input voltage here, and this goes the collector of this transistor, which is called Q input, the input transistor, okay, because it's connected to the input. And this goes to the base of my Q1 transistor, and this is my emitter, which is connected to ground. And then I have here to the collector, I have the RC, this is here RB, okay, and here I get my output voltage. All right, Now, beautiful. Let's see the first case. What is the first case? Let's apply Vn. Okay, case number one. Let's use red color here. Case number one, which is this case here. Okay, my input voltage Vn plus VCE, VCE saturation, of course, for this transistor is less than the VBE forward active for this transistor. So in this case, this transistor, which is Q1, is in what situation? It is in the cutoff. Okay, so if it is cut off, it means that the current here that flows through the RC IC equals 0, which means VO equals what? VCC, which is 5 volt. Okay, and I can see this very clearly, right? You can see the output here value, see the output value here and the axis. All right, now what happened if I start having this V input instead of less here? Case number two, let's choose another color here. Case number two, that V input plus VCE, okay, saturation for this transistor, okay, equals VBE, a forward active for this transistor. Meaning, let's say for example here, if this is zero point 0.5 plus zero point 0.2 equals 0.7. Okay, volt. In this case, what happens? Well, in this case, this transistor Q1 will be forward active, and therefore, what I have in this forward active, I'll have a current which is non-zero, right? It is equal actually beta times IB, and VO equals what? Well, the VO here equals what? It is equals VCC minus IC times RC. Okay, all right, that's very straightforward. And let's take a look at the third case. Okay, the third case, when I have, well, let's choose more distinguished color. The third case is that when I have the V input plus the VCE of this transistor greater than the VBE of this transistor. Let's take an example, numerical example. So let's say this is VI is 0.6 plus 0.2 volt, of course, all are volts. That is greater than 0.7, okay, volt. So in this case, what is the situation for Q1? Q1 will be in saturation. If Q1 is in saturation, that means what? Well, that means the value of this output here, voltage, to the ground is 0.2 volt. 0.2 volt. And you can see here, if I am above 0.6, you can see what's the value of the voltage here? It is 0.2 volt. Okay, all right. And clearly you can see how this we manipulated the case, we manipulated the status of the transistor using the input. That is the trick. Okay, all right. Okay. Yeah. All right. So here we can see that there is some kind of parallelism between controlling this Vx point, sorry, controlling the Vx point in the DTL, and controlling the Vx, okay, let me restate this again. We use the input to control the VPE here, and here we use the input to control the VPE. Now, in this case, through back-to-back diodes, and in this case, through a transistor. Okay, so there is a parallelism here between the two methods. Okay, so and here it shows how I can implement a NAND gate, how I can implement a NAND gate using or in the TTL in the TTL family. Uh, Basically, if any of those, oops, sorry. Let's get this thing. Okay. All right. If any of those inputs, oh, I keep doing the same stuff here. Okay. Let's see if I can presentation mode. Okay. Now, if any of these inputs here is low, any one is low. If anyone is low, meaning what? What do you mean by low? It means that any one of these inputs below zero point 0.5. This means this point will be less than zero point 0.7, forcing forcing this to be in an off state, and therefore the output will be at high. But if all of them, let's get another color here. Oops. If all of them If all of them are high, 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 meaning, what do we mean by high? All of them at zero point 0.6 or more volt, right? Then this transistor will be in the saturation. I'm sorry, yeah, would be in saturation, sure. I'm going to maintain a zero point 0.8 volt here, okay? And this will be in saturation, which means that the VO is in the low state, okay? All right. Okay, so let's move on to the next family here and the final one. Okay, the final family is called ECL. And basically, the idea of ECL is that the output transistor, which is this one, okay, is is placed in two states, either cutoff or forward active. It doesn't go through saturation. And you can see there is a kind of a mirror type of implementation. A resistor here, a resistor here, transistor here, transistor here, and then a current source. A current source, typically this is a resistor. Okay, and let's go to the next slide, really, where we have more interesting analysis. Okay, all right. So basically, in this type of logic, you have here the input side. Okay, and then you have a reference voltage. What do you mean by reference voltage? It means the following: if the input voltage is greater than the reference voltage, right, then the input voltage, whoops, sorry, then the input voltage is considered to be high. If the input voltage is less than the reference voltage, then the input voltage is considered to be low. Okay, that's what it means. So for example, let's just give an example. Suppose, for example, this is 0.5 volt, right? If V input is zero point 0.4, the input is considered to be low. If V input is zero point 0.6 volt, then zero point 0.6 is V input is considered to be high. So so this is the important reference voltage. Now, and therefore what we say is the following: said, notice that if V input is less than VBB, which means what? Which means V input really is considered to be low. Now, if this is the case, you will see that the transistor here, it will be in the off state. If it is in the off state, means what? Meaning this will be connected to VCC and it will be high. And what is Vn? It is the inverted output of this one. So this is now we had it as low, the input, the output is considered to be high. It turned out ECL has two outputs. There is the output and there is the non-inverted output. So what happened to this side? Well, on this side, this transistor is not, it's in the forward active state, and there will be a current flowing through this resistor, which is dropping this voltage so that it will be low. Why the voltage of this node is dropped to be low? Because V input will be equal to VCC plus, VCC equals V non-inv, which is this one here, plus ICRC. Now, as long as there is a current here, why there is a current? Because this guy is a forward active. Then this will be small and will be low. Okay? Similarly, we can consider the other case. All right, let's see. Okay, we can consider the other case. What other case? Where if the input is greater than the reference voltage, therefore the input is considered to be, oops. Okay, so the input is considered to be a high, and in this case this will be in forward active and this will be off. Now therefore this V non-inv will be high because there is no current here. This is zero, so this node will be connected to the VCC, and there will be a droppage voltage here, so that this will be considered low. So notice that high, low, high. That's why we call this node the inverted output and this node the non-inverted. Why? Because the non-inverted mirrors the input. So this is so this is the inverted and non-inverted. If this is low, this is high. If this is high, this is low. Okay. All right, so this is how this operation. Now notice how this current mirror that was in the previous slide, we implemented using a small resistor, okay, to allow current to flow through it. Okay. Now, okay, let's see if okay. Now, here is an implementation of an OR gate, an OR gate. This is the inverted output and the non-inverted an OR gate. So this ECL has always two outputs, the inverted and the non-inverted. And it's very simple. Basically, if any one of these guys, the transistors, if any one of the inputs are high, okay, so if any one of these inputs is high, then we really allow the current to go through this, meaning that I'm gonna drop this to be to a low and this is high. Because if you have a current flows through this resistance, this resistor, then you are dropping the output value to a low. If both of them are low, then there is no current here and this becomes a high, this becomes a low for the output. Okay. All right, and with the ACL, we conclude our discussion for the BGT family, BGT and diode family gate implementation of gates. Thank you very much.